So last video we have wasted a lot of time trying to explain this portion over here. Okay, so now this video I'll just explain why we actually choose our particular integral as our forcing function. Okay, and typically in any second order differential equation you will choose this as your particular integral, and then you differentiate two times. So in this video we're gonna explain why we actually choose this and differentiate two times also. So therefore okay, so as we explained in the very first part of the force vibration, okay, we say that you would this is the chop analogy we talked about it last time. So when you pull this mass down, okay, over this to this position over here, okay, to this position over here. At first, the very first one you need to pull it down with the time taken to pull it down is kind of okay. I just show you the motion. Okay, so when you pull it down, like that, and then you will start to go faster and faster, right? So typically the starting portion, okay, the starting portion when you pull it down, the time taken for it to oscillate one time is kind of like um longer than when it's steady state, because you have to overcome the damping and the spring that is opposing the forces itself. And then when it achieves its momentum, the velocity comes in. It starts to go faster and faster. So in this concept, this is why we have explained we explained this thing. Okay. So in steady state, object will somehow have a frequency same as the driver. So in this case, you actually oscillate in this form. I mean frequency. Okay, this is the amount. Okay. Yeah, anyway. Yeah. As the frequency, as you know, is f equals to 1 over period. So period is equals to 1 over f. So the amount of frequency within one period is how much. Okay, so it is also dependent on the in steady state says that the frequency itself is the same throughout, and also that the amplitude itself is the same. So the amplitude itself is the same, and the frequency, okay, the frequency how much is oscillate per wave, I mean per period, is also the same. Okay, so I hope I made this clear. Okay, and then with this concept, this is why we can actually use this as our forcing function, and we are analyzing in terms of the steady state in this case. Okay, so in this steady state, we can use this formula, and then we differentiate two times. Why we differentiate two times? Because if you differentiate as shown here, this is the equation of our forcing function. Okay, we will explain why we actually choose our x to replace the f. Okay, because they are proportional. You differentiate one time, you differentiate two times. Okay, and this phase angle is just saying that it may be due to certain other aspects of things. Maybe they put on weight or whatever. Okay, assume mass constant. I don't know or whatever, but yeah, this is something I don't know how to explain. But nonetheless, they put it in, and give me a moment. I think just to account for other loss. I mean, external stuff that comes in that may affect the system itself. Maybe some resistance or what, or maybe you put on new stuff on it. I don't know. So anyway, so where x is the amplitude of the oscillation, okay, as we mentioned, this x, and then this one is the phase of displacement. If you in the future you understand, then you can just post a note about this, and then sub back into E1. Okay, so we sub this to all this thing into E1, which is this one. So if you remember, uh, first you differentiate two times, and then you sub the second order into here, the first order into here, and then the forcing function itself into here. Okay, so we do the same thing. So to take a look. So this portion here, okay, we just sub in over here. Okay, we just sub in over here. We are so this portion, okay, it's over here. I mean, sorry, it's over here, and then we plus. So maybe I should indicate it in a more clearer way. Hold on a while. What's my pen? So this portion is this, right? It's the same thing. Okay, they are the same. X double dot is equals to this, and then X dot is equals to this thing over here. Okay, minus WX, and then I didn't change this, they are still here, and then double n square, natural frequency is over here, while x, okay, while x is over here, which is the same as this orange color dude over here, and then the forcing function is still the same over here. So we're just trying to solve for an equation to solve for the particular integral. So as you can see, this one is negative and negative. So because this is plus, so I mean we are just summing up all the because our equation itself says that it's plus, right? Everything is plus. So this is why we follow. But however, since this is negative, therefore it just rearrange. You get this negative over here. Okay, just get the negative over here, and then the negative over here also. So you rearrange everything. You just bring the negative. I mean, you bring this whole chunk of stuff. Okay, this whole piece of big thing. You just bring it over here. So you make this equation 0. Okay, you get what I mean? So therefore you get we call it equation 2. Okay, so now here comes an important understanding again. Okay, so this is a very hairy formula. Okay, we don't know how to solve. You see, this is the first time you see such a big chunk of particular integral. You don't know how the hell you want to solve it, right? So one thing is to actually because there is cosine and sine. So if you were to go and take a look for before I talk about it, we have to make sure everything is in terms of cosine. Okay, in terms of cosine. You can do it in terms of sine, but it's because as you know, sine and cosine, they are related. Okay, based on the trigo, sine x is equals to cosine x plus pi over 2. Okay, I mean minus sine x is equals to cosine x plus pi over 2, and plus sine x is equals to cosine x minus pi over 2. Okay, that's the sign convention difference. And then why we actually choose everything equals to cosine. Okay, as you can see, the graph itself. Okay, cosine graph starts from 0 point. Okay, cosine 0 equals to 1, right? Sorry again, I thought, sorry. Okay, so let's drop that explanation. Okay, I made it wrong. So why we actually change the sign to cosine is just because there's so many cosine over here. Okay, there is only one sign over here. So in order to do that, we actually change the sign to cosine first. Okay, and then because eventually you want everything to be the same, and then you can do something with it. Okay. So what do I mean do something with it? Okay, eventually we have to solve in terms of a vector polygon. Okay, so the vector polygon is for example a plus b. Okay, a plus b is in this direction, is equals to this one, a plus b, and then a plus b plus c is a plus b plus c is equals to this line. A plus b plus c plus d is going in this direction actually, is equals to this line over here. I mean this line over here. So a plus b plus c plus d is equals to this one. So in other words, a plus b plus c plus d, we will get back to this point. So this is the vector polygon method. So why they actually want to change sine to cosine? It's just simply just don't want to confuse in terms of sine and cosine. It's, I think just for the sake of neatness, so they actually changed to cosine. So I talk so much about changing sine to cosine, but I haven't tell you how to do it. So we can solve by using a reduction formula. Using this formula over here, we just switch sine to cosine only. That's all, and then we substitute that into equation 2. So equation 2, as you can see, is this one. Okay, it's the same thing. I just copy this portion over here into here, and then we say we need to change the sign to cosine. So this sign is being changed to cosine. Right? So maybe I am wrong hold again. So I forget to put in this one into here. So this sign is equals to this cosine over here. I didn't change anything for the rest. Here, as you can see, everything are the same. This one is equal to this one. This one is equal to this one. And this one is equal to this one. This one only I changed this one only. Okay. And then the next thing is to actually after subbing in our angle, sine and cosine, okay, sine into cosine. What we can do is to further simplify the whole equation. Knowing that we don't want, because we don't want any fraction we don't want any fraction coefficient in the whole equation, which is this root over here, right? So this is a very key concept I want to make known. So here, so the first part actually we talk about particular integral is equals to the forcing function. Okay, this is where we started off saying that this one is equals to our forcing function. Okay, this is this one. And then we don't want any fraction as coefficient, okay, and then we make sure all are cosine and all are sine, so we don't want cosine or sine together in an equation for the vector polygon, okay. So I don't know much about vector polygon yet, so later maybe I will explain. And then nonetheless, we can further simplify this whole equation because we have this fraction over here, right? So we multiply the whole equation by m, okay. So you will eventually get this one. So the m now is being multiplied into every part of this equation. So as you can see, underlined by m over here. And then you can also further simplify by knowing that you know these are the two equations you will be using often, so you better remember. So this is the damping factor, and then this is the natural frequency. You just sub in. So make sure you don't confuse yourself with the omega angle and the natural frequency. Okay, so you have to denote by m, and therefore as you know, if you bring this thing out here, it's equals to c, right? So this is why it is c. And then if you bring m multiplied by omega n squared, you get k, right? So this is over here. So you have simplified the equation to a slightly neater one, although it's still very hairy. At least you can see there's pretty neat. The cosine are all the same. They are all cosines. So we can deal with it in a more easier way when you're plotting the vector polygon. And then the constants are being set up in a more easier way. And then with this, we are much ready to solve using vector polygon. So just to summarize before I end the video is that how we have used this set of step-by-step basis to actually help us to solve. And then the first part of the whole system for force vibration is pretty straightforward. Okay, you draw your free body diagram, you understand the movement, draw FBD, and then you do summation, you set up the equation. So typically always is the fourth part is the most tedious part. So you set your FBD, you set the summation, and then you eventually get this thing. And then this one I assume you already fully understand. It's pretty easy. Until here, now the complicated comes in. You have to know your complementary function. You have to assume certain facts, particular integral also. And then this is the portion is a very vital one. If you can't set up, you're dead. And then you choose your complementary function. You choose your your particular integral. And then you try to set up an equation for a particular integral. So far all we are doing over here is actually to set up particular integral. Okay, so at the end of the day, if you have some equation for here, you have to add up to this one in order to get your x position. Your x distance. Okay. So I hope I give you a very clear understanding so far, except this one, the theta, alpha or whatever. So this angle here, they say is a phase of displacement. So I will leave you to go and find out. Okay, so we'll see you in the next video for vector polygon. Bye bye.